Hey everyone, and welcome. Today we're going to get up close and personal with a really fascinating mathematical shape, the cubic function. So let's dive right in.
Okay, let's kick things off on some familiar ground. You've definitely seen this U shape before, right? It's a parabola, which is just the graph of a quadratic function like x squared. We're going to use this as our anchor point for today's journey.
So what do you think happens when we take that simple x squared equation and we just crank up the power from a 2 to a 3? Well, as you're about to see, things get a whole lot more interesting.
To really get a handle on that shift, we first need to understand where these functions even come from. We're moving from squares to cubes, but it turns out they both live inside the same big polynomial family.
So what in the world is a polynomial function? Well, think of it like a giant family tree. It's got the simple, straight lines, the familiar parabolas, and of course, our star of the show today, the cubic function, plus all of their higher-powered cousins.
And the names themselves actually tell a great story. Quadratic, which is our degree 2 polynomial, comes from the Latin word for square. Makes sense, right? Length times width gives you the area of a square. And cubic, our degree 3 polynomial, gets its name because those three dimensions, x times x times x. That's exactly how you find the volume of a cube.
All right, now that we've met the family, let's properly introduce ourselves to the cubic curve. We're going to start by graphing the most basic, fundamental version there is. F of x equals x cubed. Whenever you're dealing with a new function, the absolute best way to understand its graph is to just start plotting some points. So we'll take a few simple x values, cube them, and see what we get. And hey, pay close attention to how those negative x values give us negative y values. That's a huge clue about the shape we're about to see.
So now we just take those points from our table and pop them right onto the coordinate plane. See that? You can already see a shape starting to form. And whoa, that is definitely not the parabola we're used to.
And when we connect those dots with a nice, smooth, continuous line, there it is. That's the cubic function's signature S-curve. Look at how it rises up from the bottom left. It kind of flattens out for just a split second at the origin, and then it just keeps shooting up toward the top right.
Let's break down the key features of this new shape. First off, its domain and its range cover all real numbers. That means it goes left and right forever and up and down forever. It crosses both axes right there at the origin. And here's a huge difference from the parabola. It never ever turns around. It's always increasing.
And now for the main event, a little shape showdown. We're putting our new cubic curve head-to-head with that familiar quadratic parabola. It's a tale of two curves.
So let's start with what they have in common, their shared family DNA, if you will. Well, for starters, they're both polynomials. They both have a domain of all real numbers, and they both pass through two very important points, the origin at 0, 0, and the point 1, 1. But the single biggest difference between them, it's the range. The parabola, it's kind of like a bowl. It has a bottom, a minimum value, and its y values can only go from 0 on up to infinity. The cubic, though, is more like a winding road with no floor and no ceiling. Its range is totally infinite in both directions.
Okay, but this is where it gets really cool, when we lay them right on top of each other. You can see they cross at the origin and then again at that point 1, 1. But in between those points and everywhere after, their behavior is completely different.
Let's call this the crossover story. For any number bigger than 1, the cubic function just explodes. It grows so much faster. I mean, think about it. 2 cubed is 8, while 2 squared is just 4. But, and this is the kind of weird part, in that tiny little space between 0 and 1, the opposite is true. The quadratic function is actually higher than the cubic. For example, a half squared is a quarter, but a half cubed is a much smaller 1/8. Now, if you've ever had to shift a parabola around on a graph, I've got some great news for you. When it comes to transforming the cubic function, the exact same rules apply. That's right, those rules you learned for shifting, stretching, and flipping graphs are totally universal. For cubics, we use this general form you see here, where k controls the up and down movement, h controls the side-to-side shift, and that a out front handles all the stretching and flipping. Let's see it in action. If we have y equals x cubed minus 3, that minus 3 is our k value. And just like you'd think, it takes the entire original graph and just shifts it straight down by 3 units. Simple as that.
And what about a horizontal shift? So if we graph y equals the quantity x plus 3 cubed. Now remember, the number inside the parentheses can be a little tricky. It does the opposite of what you might expect. That plus 3 actually scoots the entire graph to the left by 3 units.
And of course, we can combine it all. In this one, the negative sign out front flips the graph completely upside down. Then the -1 inside shifts it to the right by 1 unit. And finally, that +2 on the end lifts the whole thing up by 2. See? It's the same rules, just on a new curve. So let's zoom out one last time and look at the bigger picture here. You might be starting to notice a pattern in all of this. And that's because, you guessed it, it really is all in the family.
And honestly, this is the big idea I want you to walk away with. Those similarities we found between x squared and x cubed, those patterns hold true for all the basic parent functions in the polynomial family, x to the 4th, x to the 5th, and on.
Which brings us to a final little brain teaser to leave you with. Now that you've seen the relationship between an even-powered function like x squared and an odd-powered one like x cubed, what similarities do you think you'd find between two odd-powered functions, like x cubed and x to the 5th? It's a great question to mull over as you keep exploring this super cool family of functions. Thanks for joining me today.